Hi! In this episode of ElectroBOOM 101, I talk about op-amps or operational amplifiers. Like my professor back in the university said, they are the best thing ever designed in electronics. That's true, if we ignore all other things. And you can get them as these electronic chips standalone, if not part of a more complex chip, and they amplify. Like here, I tied a microphone to amplify sound, and without loading the source signal, without any distortion, without... Oh, shit. Oh, shit. Oh, oops. This is a non-operational amplifier. Which begs the question, why are they called operational amplifier? Is there a secret society of engineers using non-operational amplifiers trying to bring the world of amplification to an end? Somebody explain it in the comments. Of course, they come with their limitations. But it is almost impossible to talk about analog circuits without including an op-amp. Here, the top plot is the microphone signal and the bottom is the output with 5 times amplification. Op-amps have made amplification so easy and accurate that they are used everywhere, like in any type of sensor signal processing and amplification, audio, video, measurements, filters, comparators, buffers, power supplies, analog math. And all it is this at its simplest form, a voltage amplifier. It takes 2 inputs and amplifies their difference by a gain so high we typically assume the gain is infinity in an ideal case. In reality, it can be well over 10,000 times, so compared to infinity, it's infinite times smaller, but it is so large that the error it creates compared to an infinite gain is negligible.
So, tell me what's been bothering you?
See, proper engineering is done with so much neglect, otherwise we go crazy.
Yes, it's quite the conundrum.
So basically, an ideal op-amp is like an open circuit at its input, so it never draws current from the circuit it connects to. It has an infinite gain and you can draw as much current as you want from its output. In reality, none of these are true, but we can work with these assumptions. You know what they say, fake it till you make it, and that's when the reality hits you. That's all. A simple thing with a billion applications. What can we use it for as is? Only one way, that is a comparator. With a gain of infinity, any non-zero input voltage difference just gives a positive or negative infinity. Oh, so this is where the reality hits us. In any circuit without capacitance and inductance, aka components that can store and release energy, the voltages of the circuit stay within the supply voltages, or rails as we call them, that power the circuit. Op-amps are one such circuit. Ideally, I said ideally! So in an op-amp where we now add 2 other terminals to show the supply rails they ride on, the output voltage will jump to the power rails and no further. So you could say the gain is ideally infinite as long as the output voltage is within the power rails. So with the single op-amp, we are just comparing the 2 inputs and our output is high or low like a digital circuit based on which input is higher. If we aim to compare only, there are comparators with the same symbol that perform better than op-amps to create a digital output. Op-amps are designed to perform better in an analog circuit, although you can use them as a comparator as we see here. I'll talk about comparators in another video. So as you can see, the output jumps to the supply voltages. As you can see, the output jumps close to the supply rails in typical op-amps with some voltage difference. Only in rail-to-rail op-amps can the input and output voltages get real close to the supply rails. What makes op-amps really spicy is when you add feedback to them, where you somehow connect the output of the op-amp to its input. You can connect the output to positive input or V plus for a positive feedback, or negative input or V minus for a negative feedback, or both. Maybe I should have had a video on feedback first before jumping into it here. But let's make it simple. For stability, positive feedback Bad. Negative feedback, good. I was once contemplating making a device where you put two spiky electrodes on a chair with a microphone and a circuit to convert sound into high voltage feeding into spikes. A person would sit on the spikes, yell, the audio turned into high voltage, the guy would yell louder, creating higher voltage, and so on. That would be a positive feedback loop. I didn't make it into a product though because I received negative feedback from my test subjects. Kept out of jail. Same goes for OpAmp. In a simple positive feedback where the output goes to V+, a tiny rise in V+ raises V out, that raises V+, that raises V out, driving it into a power rail and latches in that state, or vice versa in the opposite direction. There are great applications for positive feedback though, but unless you use it along with a stronger negative feedback, its output is digital and falls under comparator applications. Subscribe and stay tuned for the next ElectroBOOM 101 on that. What we really like for an OpAmp though is a negative feedback. If V- is slightly higher than V+, creating a negative input delta, it pulls the output back down, bringing V- close to V+. Similarly, if V- is lower than V+, creating a positive input delta, the output goes positive, pulling V- close to V+. Stability. So the output has to stay still between the power rails with a known value. This means, assuming an infinite gain, the delta between the positive and negative inputs must be zero. So we can assume both inputs are virtually shorted because their voltages are the same as long as the output is within the power rails. But as soon as the output gets too close to a power rail, all bets are off and the input delta will increase. Okay, let's talk reality. Like I said, an op-amp's output voltage hardly ever gets close to the rails and there is always a distance to the rails. The current you can draw from the output is limited. There can be a very small current draw from the input pins we ignore. There is some input impedance. There can be a very small input offset voltage and inputs are not exactly equal in a feedback loop. The op-amp gain is only very high for a small frequency range and drops quickly by frequency. The output voltage can rise like a line at high frequencies due to something called slew rate. There are power limitations, voltage limitations for input and output and supply. Dude, we need to protect our youth against too much information too early. The birds and the bees talk come later. Let them chew on the simple stuff first. Oh yeah? Then chew on this. Anyway, there are tons of fascinating circuits to be built with an op-amp. I only point to a few of them here and won't spam my channel with videos about all the possibilities. The point is to get you inspired and interested. But I was also thinking, if you are interested to learn more about op-amps or how they work in real life or any other circuit, I could sit down in a live stream for each, play some elevator music and try to analyze a circuit or two. If that's something that interests you, then toss a coin to your teacher on Patreon or join YouTube memberships and I'll stream privately for those guys, which makes it easier to interact with fewer people and answer questions too. Anyway, keep it simple. Simple works in most cases. Let's assume we have a positive and negative supply voltage large enough and a simple circuit like this. Considering the input has no current draw or loading, ideally, there is no difference between a short circuit or a resistor on the feedback loop because no current means 0 volts across the loop component anyway. The two input voltages are equal to the output voltage. This is a simple buffer. You can connect a sensitive signal to the input without loading it, that otherwise would be disturbed by even a minimal load. The buffer copies the signal at the output and connects it to another circuit that may safely draw current from it. But you can also add more resistors to your feedback path. Now you are dividing the output voltage over 2 resistors and feeding it to V-. Let's calculate what's going on here. Assuming the output voltage is within the power rails, it means the op-amp input voltages are virtually shorted or V- is equal to V+, which is V-in. Now, again, op-amp doesn't draw input current and so doesn't affect the voltage divider.
I give up.
It's accurate enough. So, like I mentioned in my other video, a resistor divider splits the voltage across it into a smaller voltage proportionally. V minus is equal to V in, so rearranging the equations we see the output is equal to input amplified with a gain only related to resistor values. This is an infinite input impedance, zero distortion, non-inverting amplifier. You can do the same calculation assuming a finite op-amp gain, but still op-amp's gain is so large that with a very good precision you can assume the overall gain is only related to resistors. In this circuit, the output and input are in phase. But what if you want to flip the output? You simply give the input voltage to the resistor and connect V plus to a fixed voltage like ground, and you get a negative gain. This is a finite input impedance. The input impedance of this is R1 since V minus is a virtual ground. Not good for sensitive signals. Zero distortion inverting amplifier. The lovely thing about the huge gain of the op-amp is, as you have noticed, in these feedback circuits, the gain is only dependent on the resistors you pick, not the gain of the op-amp itself. So the op-amp's huge gain can be distorted, change from 10,000 to 100,000 and back, or drop over the frequency band. As long as it is super large, the feedback removes the distortion with high precision or significantly increases the bandwidth of the circuit. That's the beauty of the op-amp. Take this transistor push-pull circuit. You use it to buffer. It draws small input current and outputs massive current like in audio amplifiers and such. Its gain is around 1, but it distorts the signal heavily by cutting the midsection. You add an op-amp to it with feedback from its output. The op-amp, trying to keep its inputs equal, sends signal with an inverse distortion to the push-pull buffer that passed through it creates the same signal as the input. Huge gain is awesome, and op-amp is king! Toss a coin to your teacher if you want to see more, if you want to learn more privately. Toss a coin to your teacher, fans of electricity. Yeah.